Yeah, I introduce Luca. Today we are happy to have Luca to give a talk in our ASAP seminar. That Luca is an applied scientist at Amazon Web Services, where he works on fundamental research of our next generation sequence models. His research focuses on the design of hardware-aware algorithms and the development of memory hierarchies to enable efficient long sequence processing and advanced reasoning in modern sequence modeling. Yeah, today that he will bring a hybrid method that can hybrid linear attention and other attention mechanism in one layers. The, that I think Luca can still just start the talk. Yeah.
Awesome. Yeah. Thanks a lot for the presentation. Yes. So hi everyone. This is the presentation. This is structured around multiple ideas. So I will try to give you all the insights that we developed working in this field, which is very fast and moving very quickly, and we are making a lot of progress. So I will try to give you all the insights that we developed working in this field as we move forward. But feel free to interrupt me if for any reason you have any questions. Don't wait until the end. I think it's an interactive seminar, and we want to keep this way. But anyways, awesome. So the title of the presentation is the title of our main paper, which is called the MOJO Hybrid State Space Realization of Foundational Models with Eidetic and Fading Memory. And I will describe you what these concepts mean in the context of hybrid state space models and realizations. But the main idea is that is the subtitle, which is we really don't want to forget and we don't want to repeat our mistakes in some sense. So the idea is that we are trying to give models a very long memory and hierarchies in this memory. Awesome. So, okay, cool. So before we start with the technical details, let me motivate a little bit why we are interested in this line of work. And so obviously, we need to have models with a decent memory, which can process very long sequences. And in the recent years, we have seen multiple times state-of-the-art models coming up with huge progresses and very long, for example, context windows, processing very long information and documents. For example, if you take I think this is Hugging Face, any leaderboard, you will see that state-of-the-art models typically they get a very long context for people that are used to language models. And some years ago, it was maybe 8K, a good context size. Nowadays, we are around 128K or even more. I think Gemini goes to 1 million. So state-of-the-art models are increasingly pushing for very long sequences. And we know that this is, of course, very important. And usually, recent models try to complement these with better reasoning. Now, having better memory, of course, means that you can increase the reasoning traces and the quality of them, and also access information that goes beyond the very local context that you are processing or seeing. So this is very important, and these are the state-of-the-art models that we can find nowadays. So as a very fun start, let me show you some of the results that many of you might have seen. So recently, I think Anthropic, this is Claude, was used to play Pokemon in an agentic framework, where basically the agent had to roam around and try to solve Pokemon. In this case, I think it was Pokemon Red. And obviously this is a very old video game, but it requires some long memories, a little bit of reasoning, and being able to navigate, remembering where the system or the model was and the agent was interacting with the environment. So it's fantastic that at this point in time, we are able to apply these models in these very interesting scenarios. However, even if you take the strongest or one of the best models out there, in this case, I think it was Claude 3.7, which was released very recently, you see that the system is not perfect, and sometimes navigation is hard. Sometimes the model forgets or the system forgets about where it was in the past, and then just roams around in infinite loops. So those are the kind of problems that we want to tackle with the hierarchies of memories, and making sure that these kind of agents, or if you want reasoning models, can keep track of what they're doing. Just to give you like a little bit of insight on what happened to this, what's happening in this experiment with Claude playing Pokemon. I think they, after 2 days, more or less, maybe a little bit more, they restarted the bot because it got stuck into an infinite loop. And now it's like getting back to that point. And it took like 2 days processing a lot of tokens. And typically for a human, it takes maybe, I don't know, 16 hours to complete the game. And also like kids can do that pretty easily. So I think there is still room for improvement. And that's like a strong motivation for us researchers in this field. Cool. So before like defining everything, let me start with the main idea and the concepts. So realization of memories for sequence models in this case means being able to process, like to take into account a lot of information from the past in order to predict the future. Now, the basic definition of a state, which is what we will be tackling a little bit in this presentation, is that the state of a system should be like a function, of course, that it comes from the past, so it takes into account all the past, but this function must be a sufficient statistics for prediction, which means that you are basically not leaving behind any information that is useful in any way to predict the future. The future in this case could be like the next token. In more generic settings, could be even like actions for something that is like a dynamical system or a player playing any board game. So, for example, in this case, one simple way to think about it is that the conditional probability of the next token, let's say, given the state, is the same as the probability of the next token given all the past inputs. Now, obviously, creating this X, which is the state or the memory of the system, is like easier said than done, and it leaves a lot of flexibility for us to define. In the most naive situation, obviously, you can say, let's take every single input that the system has ever experienced, and let's use this as a state. That's fantastic. Obviously, you can do that. However, it's not like compressed enough, and obviously it will take a lot of time to process, and so it's not optimal in any sense. That's why we're looking for X, which is a compressed representation of the whole past. Just to give you another intuition, even like when people are presenting like presentation or just speaking with each other, so the state of a dynamical system or like the state of the conversation or the state of an interaction is not typically fixed at the outset of the interaction. And this is very important in the sense that it's difficult to assess a priori how large the state would be before even seeing the data. For example, if someone now asks me, repeat every single word that you said in this presentation from the start to now. I mean, obviously it's not super difficult because I was speaking for maybe 5 minutes, but if you start asking for like a longer recollection, I'm sure that any people in in this situation would really find it difficult. And nonetheless, we know exactly where we are going and what the next word or token will be. So this is why we need to so this is why it's difficult essentially to build this state. Okay, so I think this covers a little bit of the intuition. So let me start with a little bit of the main benefits of modeling this kind of memory or state. So first of all, obviously, if we improve the memory of these systems by incorporating it into a fixed dimensional state or like a compressed state, we will have cheaper context lengths and we can process them more efficiently. And also we will basically reduce a little bit the reliance of ad hoc context engineering or context editing in the current systems, which usually use like heuristics to change the context, do RAG, and basically fit in a fixed dimensional context length or small one, essentially a lot of information. So this is important, but at the same time, if you're familiar with reasoning models, we know that recently there has been a lot of attention in these kind of systems where basically the basic idea is that on verifiable domains, you know that you can filter some samples that you like for the generation, and then you can upsample them, and the model can learn to basically reason through this kind of filtering or proposal steps, filtering, and then training. And this is good, but the question is, if you improve the memory and you can make it a little bit more compressed, then you can increase the amount of like samples that you can generate and verify, and therefore you can make the whole reasoning model or system much more like strong. For example, in this case, the user analogy that I use is the current way of like building this system is more like throwing spaghetti on the wall and then checking what sticks, and then basically after that only upweighting some of them. So the moment we have a better compressed memory, we can fit more samples if you want increase the n in the best of n, and then obviously have a more more scalable inference of this system, which in turn improves the results of the models. So studying memory and states in these systems is kind of interesting because you can basically reuse any results and the achievements you get along all of these axes. So to go into the meat of the presentation, in this talk, we will discuss about this paper, which is basically laying down the foundations of a lot of these ideas in a principled way, and then realizing like all of these ideas in the most optimal implementation that we can in modern hardware with the GPUs and TPUs as well. So let's start with the basic idea. So recently, like transformers, they're very standardized in some sense. They have a sequence of blocks that repeat. They are interleaved between attention MLPs. Typically, attention is implemented in different ways, either sparsely or just with a sliding window, or basically with a full attention. This is how models have been done in the past years, and this is where the field has converged, and this is more like the stationary distribution. But very recently, we discovered that we can replace some of these layers, which are obviously very important, but we can replace them and replace them with some linear attention if you want, or if you're more familiar with like state space models. For me, like they're basically the same, apart from minor details. What we have seen recently is that we really don't need a lot of attention in these systems in order to go back to like state-of-the-art performance. And many works, I forgot to add one, but like Jamba, Zamba, Samba, Griffin, and I think also Minimax 01, which is one of the largest hybrid models up to date. They have been used to basically process the same amount of information of full transformer models and replicate their performance. But in this case, they managed to achieve that only with a fraction of the attention layers, which are very expensive. Now, this is good. We like it. The question, though, is, okay, but how are these models being developed? And if you check, like it was early last year, of course, but basically what they do is very naive. So they take some attention layers, they drop them, they replace them with linear attention, they interleave them. So basically, every single model is just a minor variation of the basic same idea, which is not even a great, I mean, like a lot in the sense that they are just interleaving different layers. But the main point is that they are basically, there is a combinatorial explosion of all the possible architectures. And these new systems or models in this case, more or less fit along different permutations of or combinations of these layers. So the main question that we try to answer in our work is basically, can we replace all these like fancy blocks with one single block, which is a generalization of both attention and linear attention or SSMs, and basically go back to a more unified architecture, which doesn't require you to interleave layers and do fancy like optimization or exploration of many different architectures. So this is the main question. And so the question is, how do we build a single layer that in our work we call MOJO, that basically can build the memory of the system and decides what to keep, what to discard, and do that in a principled way. We used the language of realization theory to like describe this process, and this is the main contribution of our work, essentially. So, eidetic versus faded memory. In the title, I mentioned that we're interested in hierarchies of memory. And in the most simple way, we have two forms of memory. One is perfect, one is not perfect. So there are no other choices. The perfect one, we call it eidetic, which basically means you can access information from wherever you want in the past, and you can always recall it perfectly. This perfect recall. This is if you want to model it in your head. This is like the attention mechanism, which is very strong, but of course very compute heavy. On the other hand, you have the complementary memory, which is fading memory. And this is like a compressed form of it, in the sense that it has not, it doesn't have like a perfect memory of the past, but it is very fast and cheap. So they complement in these two directions. And I'm sure that most of people interested in this seminar, they're very familiar with this concept, so I don't want to leverage this, but remember that attention is as you process like a lot of sequences in batch form, it goes up quadratically with the amount of compute that you need to spend. On the other hand, linearized attention or like SSMs, they only need a linear cost. However, they cannot recall very information from the past very effectively. And this has been shown multiple times. And I report here one work from, I think, NVIDIA, where they are showing basically this basic insight on, I think this was Ruler or the phone book benchmark. So in our paper now, we will be discussing exactly about how to put eidetic memory together with fading memory in one unified layer in the most effective way possible. So here are the key ideas of our work. So as we process a sequence of a given length, we know that the most recent past tokens, they basically collect some information that we believe is important for processing the current sequence. And therefore, we will process it with perfect processing, which is, if you want, with attention. But at the same time, attention is limited in its span. So the blue block cannot be arbitrarily long because compute cost goes up very quickly. So for everything that goes and lies beyond that point, we need a summary. So this summary, we start our modeling by summarizing all of the past information, like if you want from minus infinity or from zero in this case, up to the last t minus k, using a fixed dimensional representation. In this call, this is the state that I was describing before. And we use a linear attention or SSMs to model this. And this is basically fading. So of course, this complementarity is not perfect because the fading memory is not perfect. We'll forget about some of the oldest inputs. And so we want a way to save some of that information for future processing. And so whenever during this processing we encounter some very interesting tokens or inputs, then we basically store them in a shifting register, which keeps in it all the information verbatim as it is from those tokens. And we call this eidetic memory. So our goal in this paper is to show how to build effectively in hardware like GPUs or Trainium or TPUs, how to basically build these two forms of memory efficiently. I think, if there are any questions, but else I can go into the details. Awesome. Cool. So this is the diagram that I usually keep in mind, which I think gives in 1 second all of the ideas. Attention is like this square wave, which forgets everything. Like linearized attention goes down like an exponential filter. And our MOJO architecture is basically combining all of these forms of memory into one. So you will have like this kind of input-output map if you want. And if you're familiar with control theory, you can call this like impulse response or something like that. Okay, so let's see how we build it. So we use the language of stochastic realization, which is a very powerful language, which we didn't develop. This is like a standard in control theory since probably the 80s or even before, like with Kalman, so probably 60s. But the basic idea is that the goal of stochastic realization is to find a dynamical system, let's call it sigma for 1 second, and its state, so its memory, such that whenever you continuously use it to generate new sequences of observations, these fit the actual observation of the system. So this basically is a very broad problem that in engineering has been like encountered so many times, and it's still like a very important problem. And for very complex systems that go beyond like linear time invariant ones, I think it's still a very open question. But in any case, even if we restrict ourselves to the most simplistic case where the system is like linear, so it cannot be easier than that, basically. You can see, if you check like a little bit of the math, that there are infinite many realizations that you can basically use to describe the very same dynamical system. So this is interesting because you can prove some theorems and basically say that so if you take the space of all the possible systems that you can model, you can basically say that there are equivalence classes of models in this case that are, even if they're different in some way in their parameterization, they actually model the very same input-output relationship, which basically means that if you apply this on an LLM, you can say, even if the memory, the representation of the memory is different, maybe it's larger because it's not effective or minimal, or maybe it's just very fancy with strange layers that you just invented, you, at the end of the day, you are not changing the expressivity of the system. And so realization theory gives us some kind of guarantees and tells us that there are equivalence classes of systems, and we want to find one representative for each, which has some specific properties that we like. So there are many, and this is like the language that I will be using. So there are some canonical realizations that are highlighting some specific properties of these systems. And some of those are called canonical controllable, other observable. So I don't want to go too much into the details, but the basic idea here is that if you want to check and control a system as much as possible, there is a specific form that you can use to represent all systems that are controllable, and the form is the one on the left here. At the same time, if you want to check the state efficiently, so observe it, which means observe the memory, there is a different form, which is the one on the right. Now, all of these two canonical forms have different properties, and if you're familiar, like those are not necessarily minimal in the sense that these forms are not necessarily the ones that are optimal in reducing the amount of flops and the cost of running these systems. And in fact, if you check like a little bit of the math here, you can define some canonical forms that are minimal, and this means they have the smallest possible state, which in turn implies that they are modeling the same input-output relationship, but they will basically reduce the amount of flops as much as possible, as well as the amount of parameters. There are also other canonical forms like balanced, but we don't want to tackle this in this case. Cool. So now that you more or less like have an idea of what stochastic realization theory means, let me try to convert some of the main findings to the modern realizations, or like the modern layers that we have nowadays. And for example, let's try to model causal attention for 1 second. So causal attention, like it's basically a shifting register where you have access to the whole window of the current amount of budget that you want to use. And then you have a nonlinear readout function, which is a softmax. So what we basically, you can prove is that causal attention can be modeled with a dynamical system, which is an nilpotent model, which you can represent in a canonical form, like a controllable one, with the equations on the left here, where basically you have the A matrix, which is a structure matrix. It's a non-diagonal one, of course, with all the poles in 0, and they have multiplicity more than 1, which means that this thing is not diagonalizable. Now, this is interesting because it's a very simple mathematical model, but gives you a lot of power to describe which systems are the same in some sense, or they lie in the same equivalence class, and you can use this. Sorry, what's that? Second. Okay, I hope. Okay, sorry. Okay, so sorry, I was saying that you can use this to basically describe the difference between the fading memory and the eidetic memory. So now let's try to describe like a fading system using the same formalism. And in this case, you can basically consider like Mamba, and Mamba, as we know, or like similar linear attentions, they basically have a diagonal dynamics. Every single channel is treated independently or grouped in some way, but the system dynamics A is diagonal. So these two systems are quite different in the sense that, as I was saying, nilpotent systems, they're not diagonalizable, while feeding memory systems, in this case, as implemented in recent hardware, like Mamba or linear attention, they are. So they're exactly two different kind of classes that cannot be modeled in the same exact way. So the question is, how can we generalize both of them in a unique way, such that at the end of the day, we can represent both of them with the same dynamical system? And this is basically the main question that we're trying to ask. If you want, I left here a little bit of details on how to construct these two realizations, but this is exactly what we were discussing. Cool. So in BMojo, we try to do exactly that. So we start with a minimal realization, which is canonical in the sense that it uses the fewest amount of parameters and flops to implement the recursion. And in this case, the functional form of BMojo is this controllable form, which basically means that we're applying this A matrix, which is input dependent, non-diagonal, to the state of the system, and then have a readout function, which is a nonlinear readout function that depends on the query, similarly to attention. So at the end of the day, this is the basic modeling class. And if you check the details, this is very similar to what in the literature of control is called, I think, Hammerstein-Wiener model. And it's a very powerful class of systems that can represent very complex models. And there is a lot of theory on that. But for the purpose of this presentation, we only care about the fact that this is more generic than attention and SSMs altogether. So just to show you now, let me try to map the BMojo architecture into a transformer and then into a Mamba to show you that this generalizes both of them. So if you take our BMojo equation, like take the A matrix and set every single row, like every single element in the last row to 0, you will get essentially a shifting register, as we were saying before, which is exactly like what an attention layer is doing, which is good. And this is basically representing it. At the same, like equivalently, you can show that Mamba can be represented in the same way. The mapping is a little bit more complicated in some sense because the last row on the A matrix, if you check, is basically with all the coefficient A's. It's not a one-to-one map. There is a little bit of like algebra that you need to write down in order to find the conversion. But the idea is that you can find a set of A0, A1, and AN in the BMojo update rule that matches one-to-one to any Mamba realization or just implementation. And this is a well-known result in control theory. So I think some of you might be familiar with that. So this is great. We show that we can, in principle, represent both transformers or like attention and the linearized version in one single framework. And now the question is, how do you implement them efficiently? And if you remember, as I was saying before, we do have like a little bit of like flexibility in the way we choose the parameterization because we have an infinite amount of equivalence classes from which we can pick. So the question is, which one is the best for implementation? And up to now, we basically discussed everything about the BMojo model up to this point, which is only like in the beginning slide, like the very last set of inputs that the model has processed. So the question is now, how can we make sure that we can access the past in an effective way? And this is the second point in the BMojo model. But before we go, if you want to ask any question, I think this might be a good time because I will not go back to the theory too much.
Actually, I have a question. Can you go back to several slides to the AR autoregressive attention part? Yeah, maybe go late some. So here you have a transition matrix, and I think in this case you are discussing about sliding window attention, right? It's not a full attention. Otherwise, the state size is like infinite. You would like have a infinite length tape to store all of this KV cache. And if it is a fixed size, then it is a sliding window attention, right?
Yeah, that's a fantastic point, and that's a very important one. So let me try to answer very precisely. So obviously, you can consider this as a sliding window attention, but I want to make sure that we understand each other in the sense that even like full attention, I agree, it's unbounded in principle, but we need to implement it in hardware, right? So at the end of the day, what we do is we allocate a certain amount of compute or budget. I don't know how many machines you wanna use for your implementation, and this is like the length of your system. So the moment you use this full attention, not even sliding window, and you process new information, whatever is like falls out of the context that you fix a priori, which is the amount of resources you can spend to run your model. For example, I don't know, the models that we discussed before, like Claude or other models, they have like 128K as a context size. So whatever is falls out of this is completely forgotten. So and this doesn't, it's not like sliding window attention, right? It's full attention in some sense. So, but this depends on how many resources you can spend on it. So this modeling here with the shifting register doesn't make any distinction between sliding window or full attention, precisely because whenever we implement this, we need to fix a given dimension because we don't have infinite memory essentially. So another way to say it, we cannot have the state of the sliding window or the full attention to grow unbounded.
Okay, so you assume that for every model, there is a maximum context length. I think this is yeah, it is true in practice because for each model there is a upper bound in the context length that it can process, and in this sense, yeah, it is safe to claim that attention has this fixed size transition matrix. Once given the upper bound of the context length, this is from your understanding, right?
Yeah, but that's exactly where like it's exciting for us to add this kind of fading memory, because if we add even just one single token or piece of the state as a fading memory system, then we can have an unlimited context, right? And that's exactly where we really want to push the envelope, because now we are not bounded too much about like the memory that we can pay, because we can compress it. And therefore we can have an arbitrarily long context size if you want, which of course will have a receptive field, which is not perfect. And the question is how to allocate this memory in the best way.
Okay, thank you for your answer.
Thank you. Awesome.
I
So
do have another question. So you can go back to the curve. So you have an exponential decay curve.
this one.
Yeah, and I was wondering that so you're saying that this sort of linear arms acts like some sort of exponential filter, right? And I think it is very intuitive for models with exponential decay. But what I was wondering, like, what if we have a model that has a data dependent decay in member-scale? Do you think this is still the case? We can still have this exponential decay pattern in this associative recall task?
Yeah, that's a fantastic point again. So I agree with you. If the system is not input dependent, the picture that I depict on the upper right is fantastically well, because it describes exactly what happens. The moment you add data dependency, things change a bit. But if you think about it, imagine the system processing left to right all the sequence. At some point, so long as the capacity of the state is enough, having like the gating mechanism is good because we can fit everything we need. But the moment the state is not large enough, which is typically, this happens quite often, whenever you get a new piece of information and you decide not to discard it, this must take, must be ingested into the memory, and the memory will basically put it together with other memory, like pieces of memory in the past, and therefore it will forget a little bit, because basically we are compressing everything in a fixed dimensional state. So even if, so the way I would picture the decay in a data-dependent way, I will basically just have a piecewise decay function, which basically goes down to 0 the moment the context is very, very long, and assuming that the signal has a lot of information. Because if the signal has more information at what can be represented in the state, there is no way you can fit it. And therefore you will have a decaying function as the standard smoothing or decaying that I represented here. But it's different.
Okay, so you are saying, so imagine we have memory slots, and each meaningful information will occupy one slot. And in the end, when the memory is saturated, the past information must be forgotten, and to accommodate new information. Do you think it's possible that several pieces of information occupy the same slot, and still the model could still have some capacity to do the associative recall, even though they have some superposition of information for some of those memory slots?
Yeah, that's a good point. And obviously, you can try to be clever about how you allocate the memory. And I will discuss a little bit about this later, because that's what we do as well. But at the end of the day, you are deciding what to ingest in the state and what not to keep there. So you have finite precision to represent unbounded information. So by definition, you need to forget something. Unless the quality of the data, like the variability of the data that you are processing, is fixed and your state is larger. And yeah, so this is I think, a very general, and there is no way around. But you can be more efficient. So for example, let's assume for 1 second that yeah, it's not all in the slide, so I can discuss now. But so let's assume, take for example a linear attention implementation, usually not a delta net, just a linear attention. You get every single input tokens, they have their own gating function, which is independent from each other. Now this means that if I see token 1 at time 1 and I see the same token at time 5, the way I update my state is the same, even if I already have that information in my state. This is what Mamba or also GLA more or less represent. And this means that the way we gate the system must be dependent in some way from the current information in the memory. And this is a key concept that I will describe also in a second, where basically the idea is that whenever some information is already in the state, you don't want to add it again, because you already have it. There is no point in wasting it because it's a fixed dimensional state. Yeah, so I think this is quite important. And for example, like also your work on DeltaNet and our work, they basically do this kind of, let's check what I have in memory, and then I decide whether to keep this information in or discard it. So long as I don't need to add information in, then my effective context length, if you want, is increased, because I'm not wasting any bit of information in my memory to get a new bits that I can already predict, essentially.
I see. Thank you for your explanation.
Awesome. Thanks. Yeah, this is a fantastic question, because this is where I was going. So we are missing all the second part of the architecture. If you check here, the eidetic memory part. And so the question is, cool. Now, if I implement this system, we have the last tokens that we always look in our context. We have a fading state, which is the fixed dimensional representation that we pick a priori. But the problem is that now we are missing something, right? Because the fixed dimensional state will forget. So how do we make the forgetting as little as possible, or as efficient as possible? And the way we did it is by a method which we call innovation selection or adaptive compression, which is exactly what we were discussing 2 seconds ago, where basically the idea is that we try to store in the eidetic memory, if you want, in the memory of the system, any new token that arrives that the system cannot really easily predict in the following sense. Maybe this is a bit like there is a lot here, but let me try to unpack it. So when we get a new token, we have our current memory, and we will basically try to predict this new token using the current memory. And the moment the prediction is small or not surprising, this basically means that the memory already contains information about it, and therefore we don't need to add this information again. On the other hand, if the prediction error, in this case, the prediction error is like a norm on the prediction, but we can implement it in many different ways. The moment that this is not enough, and therefore the prediction error is high, then we need to update the system memory dynamically and update it in some clever way. The way we decide to do that is by basically incorporating the new basis function, the new token, into the memory as an eidetic component, which in turn here you can consider it as being a new token in a set of tokens that are shifting tokens, like in a register, that are basically copy and paste from the ones that you have already seen. So this is like a very common, very powerful idea. You can check a lot of literature in the past, on adaptive filtering, on sparse line Gaussian processes. A lot of these ideas were there, and they're like information theoretically optimal. And I think it's interesting that recently people are like rediscovering these ideas and implementing them efficiently in hardware. I think this is very important and very interesting. So DeltaNet is one. I think also Titans, they do basically what we are doing in the same exact way by using like a prediction error to online changing the memory in some way. They choose a different criterion, but at the end of the day, the idea is the same. Fixed dimensional state and updating it with some clever update rule. So yeah, the overall BMojo memory is the final one that I have in the bottom part of the slide, where basically we have last tokens, fading memory state, plus a bunch of eidetic tokens that are basically token stored from the past, that were basically surprising the state or the memory when we were processing them. And that's basically the whole BMojo layer. Okay, so I left here a little bit of references, and at the end of the slides, you will find more. Double check it. I think this is a great idea, and it has a lot of expressive power for many of the models that I've seen being developed in the recent years or months, I would say. Awesome. So just to make it let's go into more details on the implementation, but this is a diagram that we used in our paper also to describe the system. It doesn't get more complicated than that. This is exactly what we did. And the question then becomes, how do you implement that efficiently in hardware? Because that's what we care about the most, right? So I don't know if you want to ask any questions on the of this eidetic memory with innovation selection. But if not, I can go and show you like how we implement these things in hardware. Okay, so I think we can go so you get an insight. Okay, yeah, this is a summary of what we discussed so far. There is one interesting bit that I want to add here, which is this innovation test basically, if you want, goes from left to right, which basically means that whenever we decide whether one token is interesting or not, we have to decide this in the past, and this does not depend on the current query. So in some sense, what we are doing here is making sure that we can fit as much as possible, as much information as possible into the state in a causal fashion, because we are never allowed to go back and check the old tokens that are not stored in the eidetic memory. This is very important because at the end of the day, this system, as implemented in this case, has a fixed dimensional state, which we dynamically allocate as long as we process new data, but we never go back. So this is efficient, very efficient, but it might have some issues whenever you change the query and ask information that was not stored in the state. And this is a common problem with all the systems that are not capable of looking back at different indexes in time whenever the query changes. And since query changes on the query for like language models, for example, is kind of like very important and happens all of the time, we need to find a way to further make the system capable of retrieving ad hoc information from the past that was not already stored in the system. And this is like the basic idea of this paper that we recently published. This is on arXiv now and is under review now, where basically we ask, okay, now we know that the attention span is limited by the amount of compute that we want to allocate. And typically the way that the attention span is allocated is by recency rather than relevancy, in the sense that we usually typically use only the last whatever number of tokens up to hardware limitation. So what we try to study in this work is finding ways to make sure that we can add to the context in retrieving from the past information that was relevant that wasn't relevant back in the days, but it's now relevant given the query. If you want to model this very efficiently, like and have a quick mental model, this is like having sparse attention. And in fact, this is the very last diagram I promised I show you on the MOJO like diagram, which is basically adding the last missing piece of information. So all the blocks from the most informative remote past up to the most recent past, the blue in the middle and the other on the right, this is the old MOJO. And what we changed there is just we add a way to basically go back in the past and retrieve just a subset of the information that was relevant given the current input. And we do that by implementing our own version of a sparse attention kernel or like implementation that is kind of efficient and needs to be that in order to accommodate like the finite hardware resources that we're given. So the basic intuition of this idea is that attention scales quadratically with the sequence length. So what we want to do is to extract to partition every single chunk in the past in different chunks of a smaller size, so that we don't pay like full price of attention. And the moment we do that, we basically create a compressed representation. If you want, this is an hierarchy. So basically now the whole input chunk 1 and 2 and n, they are summarized by one single vector or a very small vector, which is embedding 1, 2 up to n. And these are like keys for the whole chunk. So whenever we get a new query, we look at all the summaries, call them memory embeddings if you want. We compare with them the current query. We check which ones are more relevant. And then these are compressed representation, so we don't want to use them directly. So whenever we find the most interesting index or chunk, we just go back, retrieve from the past the chunk that we believe is most relevant, and therefore use these tokens directly in our current sliding window or like attention window. And this is like the basic idea. It's like a hierarchy of attention, and implemented it efficiently to reduce the cost essentially of processing these very long sequences. I think you might be familiar with some of those ideas also recently. I think in February, like 1 week ago or something, DeepSeek, they came up with this new idea of native sparse attention. That's a great paper. Suggest you to give it a pass. It's a very like low level implementation, like how to make it very efficient and scalable. But the basic idea is basically the same. And you need to summarize things in a hierarchical fashion in order to go back and look to information that was relevant only after you get the query and never before. This is their implementation, but and I mean the diagram maybe is a bit difficult because it's not exactly, it's the opposite of what I showed before. But if you go in the paper and go line by line, on the like on the left there is our like implementation, on the right there is theirs, and you can check that every single step of their computation is basically mimicking like the same idea. So we have a KV compression, we have some definition. The KV compression is the one used to compress the blocks into one memory embedding. And then we have the importance score, which we find with or we retrieve or compare with the current query. Then we rank stuff and retrieve them. And then at the end of the day, we aggregate all of this information into one single attention call. which is basically taking the final answer for the system. Yeah, this is very interesting, and we I think it's very related, and we are comparing this method with ours to check which one is like more efficient and more like expressive.
I have a
So
quick question.
awesome, go for it.
Okay, so did you save the entire historical KV cache for every trunk?
Yeah, that's a very important
Okay.
point. So the idea of the sparse attention is that you're never allowed to forget. So basically the KV cache remains the same. You are just reducing the amount of flops.
I see. So I was also wondering, like, in the expansion span case, you also implement some sort of query-aware KV block selection mechanism that is very similar to native sparse attention and MOBA recently, right? Yeah. So your this selection module is basically the same as MOBA or more similar to native sparse attention. So their difference is like so in MOBA, each query head can select its own disjoint set of KV block, but in native sparse attention, they impose a restriction, and that the queries within the query group must be selecting the same set of KV blocks in order to save I/O cost. So
Yeah,
so
that's a
is
good
your
point.
implementation more similar to NSA or MOBA? I'm very curious.
Yeah, it's I would say in the middle, in the sense that we do a little bit of everything. So of both, in the sense that the main difference with NSA is that if you check the first line here, the KV compression, they do use this function called phi, which is only a function of applied on the K or the V without the query information. What we do instead is that our compression blocks, if you want the indexes, they depend on the queries associated with them in the past, which basically means that we are creating the indexing, taking into account the query that was used to process the information up to that point. That's the main differentiation, which basically is a way to say, look, sometimes some context has been repeated. We don't need to have the same exact block repeated multiple times, and having this information will basically discard it, which is not present in NSA. So this is one difference, but getting back to your question, I think NSA does also a little bit, so they share the same chunk because they don't want to, so they split across the dimension of the heads, because that's the way they chunk in some sense, not along the sequence length, but along the head dimension. That's why they need along like multiple heads, because they want to fully utilize the hardware. But then at the same time, they obviously cannot allow the system to pick one single token. They need to pick like different chunks of tokens. So in our implementation, the first implementation we tried, we did exactly as NSA. So we don't have different different heads in some sense. They cannot change the retrieved KV essentially. So it's very similar, and that's the only way. I mean, this is I would say the only way you can really effectively use the current hardware to make this sort of retrieval, because you cannot change the sparsity of access to the memory. So yeah.
Yeah, thank you for your explanation. I
Awesome.
think Simon has a question for you.
Yeah, I have this is Shane speaking. So could you please go back to the previous page? Like
This one or the diagram?
previous one. But
Previous. This one.
yeah, yes, yeah. So yeah, I kind of if my understanding is correct, you are saying that in the original B module you have the most informative remote path, but this one is selected by but when you do this selection, you cannot look back, right? Because it's selected by some linear attention. So so once you want to, you cannot bring something back to the attention. So you have here the sparse attention that allow you to look back and to select the relevant key cache that can help the next word next token prediction. I like that, and so in this diagram it seems like you have 4 different type of like tokens or key cache or something. I'm thinking like does it mean they can really work complementary to each other? Because to me the look back attention, the look back selection or the sparse attention is somehow more general than the one in the most informative remote path. So basically my question, like, do we really need both of them in the same time?
Yeah.
Like why do you think they can actually complementary to each other? Because I feel like the dark blue one is more powerful than the light blue one. Yeah.
Yes, that's very true, and your intuition is correct. The main difference, though, which is a bit subtle, but I think it's relevant and why we like it, is that the most informative past, I should have numbered those, sorry. But anyways, the most informative past is complementing the fading state, which now means that the fading state, in some sense, is coupled or tied with that in most informative past, because the way it's built it's dependent on it. So you cannot throw away that information. So a simple way to think about it, if you really want, is okay, consider the red block like containing also the most informative pass in it. And this is the summary of the remote past, which contains eidetic and fading memory, but still it cannot have access to the whole stuff. So this is the main point, I would say.
Okay, thank you.
But I agree with you. Yeah.
Oh, we have another. So okay.
Yeah, hi, Lucas. Yeah, thanks for your great talk. So I'm wondering, like if we compare two family of efficiency approaches, one is sparse attention, one is a linear transformer. Yeah, seems like now the sparse attention family shows much better performance than linear time, right? So what's your opinion on this? Yeah.
Yeah, it's, I mean, I think this is obvious, right? In some sense, linear attention is a compressed representation. So I don't have any doubt that the sparse attention is, some sense, more powerful. The question, though, is how much are you willing to pay for it? Because in order to have sparse attention, you really have to store every single KV cache in the past. And therefore, if you cannot afford it, then, and your context length is limited by your hardware, then you need some clever way to expand it. And it cannot be sparse attention, because sparse attention, as we were discussing with Songlin before, it requires the whole KV cache of the past. You can compress it, true, but at the end of the day, you need it. So I think this is the main differentiation.
Yeah, so in your mind, the problem of sparse attention mainly about the storage or memory, right, for the historic information.
Yeah, so sparse attention for me is not saving any memory, is saving just compute.
Yes, that's correct. Yeah, and my second question is like, so like mobile, where we want the new network to learn everything by gating by itself. So I'm wondering, like, how important is the human prior here? Like, how important is that we design, oh, we should retrieve, we should select whatever, and what if we just let new network learn everything by itself?
Yeah, and why do you think we are not letting the system like selecting what?
Yeah, because I feel like still we have some rules, right? We define some stages, some steps, and we we divide the context length into several parts. That's you might mind some kind of human prior.
I see. So like the chunking. So for example, why should I chunk this way or I shouldn't chunk?
Yeah, that's right. Yeah.
Okay. Yeah.
I think it's hardware efficiency consideration, right?
Yeah. So I think this is more like an hardware bound, in some way. So for example, very naively, say that you want to implement this in Triton, or actually, honestly, in any other like hardware, like TPUs, training, or whatever, you know that memory is local in some sense, and accessing memory in chunks that are contiguous in the memory locations is much, much, much more efficient. If you try to do something more clever, if you want, yeah, you can try, but don't expect it to be like very, very efficient. So at some point, you need to decide which consideration you want to push for. Do you want to scale, or do you want to be clever? I think that in these cases, finding the right balance, like chunking, for example, which is completely arbitrary, I agree, but feels like the right trade-off given the current hardware we have at our disposal.
Yeah, thanks for your explanation. Seems like all such design are due to the constraints from the hardware we have got. Yeah, thank you.
Yeah, actually, yeah. Sorry,
Yeah,
Sandy.
yeah, I have another question. So in terms of like imposing the inductive bias, so sliding window attention here is like an inductive bias because for language modeling, there is a very strong recency inductive bias. So for example, in native sparse attention, they also have a branch that is basically doing sliding window attention. And I think in another paper, the MOBA by Kimi AI, and they show that they don't want to enforce the model to choose the sliding window block. They let the model to choose blocks by itself. There is no restriction at all, even though still we have some blocking, but we do not force the model to choose the latest block. And they say that this is like just like a stochastic gradient descent to decide which block the model should choose. And in this sense, the introduction of the sliding window attention block is like a more and there's more inductive bias by human beings, and so from the point of view of hardware efficiency, like aiding this sliding window attention or not does not change the total efficiency. It's more like an inductive bias, right? I want to know your opinion.
I mean, if we're building LLMs, we know that they mimic the way the LLMs, I mean, on language, obviously, like just on language. I mean, the way we speak, the correlation, for example, if you need to tokenize, you know, like some words are very long, some are not, but some words are long, so they need to be like they will have multiple tokens associated to the same meaning. But also when we speak, like we have sentences, like all the context that we're using is a lot. There is a lot of I think in some of our older works we called it contextual pressure, which means that there is a lot of locality, right? So if you want to do an LLM, I think having a little bit of sliding window to ground the system to the past few whatever number of tokens is important. And I agree, it's an inductive bias. If we have to do the same for images, for example, okay, then this is completely different. Now you have locality in 2D grid, and it depends on how you define it. But for language, I think having this sliding window attention, if you want, at the beginning to ground the system is kind of important.
Yeah, okay, thank you for your explanation.
Yeah, thanks.
Yeah, and I think I have a question because that we know that for native sparse attention or maybe the span works. The problem is that maybe for the selection part, if the context length is very, very long, it's just maybe divide maybe a constant for it so that it still scale linear with the context length. Do you have some idea about maybe how we can further improve the generalization on this part? Yeah.
I think it's this is a very important question for designing this kind of sparse attention. We are thinking about some ideas along these lines. At eye level, the obvious thing that one can assume if you follow like the presentation I'm trying to convey here is that at the end of the day, if you want to be, if you want to have eidetic memory, which means perfect recall, you shouldn't compromise too much. So you need to procrastinate the decision as much as you can, essentially. And whenever you get the query, you do your bookkeeping and you go back. Now, if you cannot afford that, I think there are many ways to compress the KV cache. So you can reduce it, but in principle, you cannot like decide a priori. how much you can discard. Because if every new token is completely different, you cannot discard anything. If every single token is a repetition of the previous one, then okay, forget. I can index it in a clever way. In literature, like our innovation selection, I think not exactly in the way it's implemented here, but as a high level idea could be a way to implement this idea, also for sparse attention. And there is a nice algorithm, the Lempel-Ziv, I think, for adaptive compression, which basically creates a new dictionary whenever you get a new information in some sense that is not already in the previous set of known information, which I think is motivated us in our work, but could be exploited also to compress even further the KV cache on sparse attention.
Yeah, I think it's because that for the selection part that it can be something like an approximation. We do not need a so accurate search algorithm. And based on the search algorithm, I think something it can be maybe sublinear, maybe something like O-log. Yeah. But I see a challenge of the KV cache compression is that because that the KV cache it is time dependent. So that maybe you need to model them maybe from left to right, so that maybe some traditional retrieval method maybe encounter some challenge, I guess. Yeah.
Yeah, for sure. Also like positional encoding.
Yeah, because
Yes.
that it's hard for you to random select some KV cache and compose them into a cluster. Yeah, maybe you can just do them in a trunk wise. I guess here are some challenge and difference in comparison with the previous one. Yeah.
Yes.
Yeah, but I think it can be sublinear. Yeah, instead of maybe a constant compression ratio. Yeah.
It can also be approximate. I mean, you don't really need to be so perfect sometimes, but in principle, if you want to design an algorithm with some like criteria in mind and not like just changing stuff and trying heuristics, I think it's important to have a clear distinction between eidetic and fading and finding the right balance with the right terminology to describe what you are trying to do.
Yeah, hi Luca. Like, yeah, I just suddenly realized one point. Like, from my question, I think I really like the design because I feel like the sparse attention selection is kind of different to the most informative remote pass. I mean, the main difference could be when you do the most informative remote pass selection, it's a token-wise selection, even it cannot look back, right? But it still select at the token granularity. So hopefully it won't miss any information, important information, but you cannot guarantee because it cannot look back. You never know what you need in the future. You can just make some guess, right? But for the dark blue one, the sparse attention, although it's very powerful, it's it can like look back anything, but it's operate at the chunk granularity. So it could miss something because let's say if your trunk size is 100, there's only one token is important, maybe you will miss this one because the trunk importance is not that large in this scenario. So yeah, I just want to add something that I suddenly realized inspired by your answer. But yeah, I think I really like this design.
Yeah, thanks. That's a good intuition. Yeah, thanks. Okay. I think I may just want to like try to finish a little bit on the technical side, and then we can finish. But I wanted just to share very quickly some ideas on how to implement this efficiently, because obviously at the end of the day we want to implement it, right? And if it's not efficient, there is no way to go. And so basically, most of you must be familiar with this or might be. So let me try to recap it so you understand a little bit my framework here. So flash attention on the left, Mamba or linear attention on the right. A is like the attention metrics, or call it generalized attention metrics for the Mamba, which is not exactly the same, but this is like the attention metrics, and the Q are the queries. So whenever you get a new query together with the K and V, you generate the block A for the attention, and then you get the query and you do those softmax, and then you get the output of flash attention with the values. For Mamba, it's basically the same, but you remove the softmax more or less, or linear attention. Now, flash attention, the second stage, you get a new query, and then you need to look back to two blocks, right? This is a chunked implementation, right? So you get the chunk queries, you go back to the K and V for chunk 2.2, then chunk 2.1, and then you do your stuff. On the other hand, Mamba or linear attention, they at the same time, whenever they process the first chunk, they compress them into a final dimensional state, and then you get to go in a single step to the new block, and then you keep in mind the past state, and then you go. So basically, after a couple of iterations, this is the main difference. So basically, the flash attention, you get to go along all the blocks again, and this means that basically you need to do that with 2 for loops because you need to access a memory multiple times. On the other end, even if you're not materializing the attention matrix, you still have to go over all the blocks. But the Mamba or like linear attention implementation, they don't, and in some sense they can implement it by one single for loop with respect to 2 for loops in the flash attention. So this is like hopefully like intuitive enough for you guys. But now the question is, how do we implement BMojo with these ideas? And this is like the first part of BMojo, which I described in the first part of the presentation, the one in the paper without the eidetic memory. And basically the idea is that now we have a sliding window attention, and we have the state, and this is very easy to implement with the current kernels and flash attention and machinery. And the basic idea is that now we are complementing the sliding window, if you want, which is a fixed cost with our state, which compresses all the information before. But if you want to implement the BMojo, the true BMojo, if you want, you need to spend a little bit more effort. So even if you basically can repeat the same process for half of it, at some point you need to store the interesting blocks or chunks, as we were discussing before, and those are like the complementary ones. And so at this point, you will find yourself with, let's say, a flash attention, if you want, kernel, where basically in every row you have the last K blocks for the sliding window, the state of your system, and another shifting register of the past interesting blocks that you processed in the past. And this is aggregated for the next token. And so at the end of the day, even if we still need to go back to get some information, this implementation is not like flash attention, if you want, which is quadratic in the number of in the flops, if you want. This is like constant or linear in the sense that we have a fixed number of blocks that doesn't grow, and we can always like mix and match information using the state and the eidetic memory all together to get to the final answer. And this is much more efficient depending on how large the context is. You will get different trade-offs essentially. And if the context is very long and your current BMojo attention in some sense is not that long, then the gains with respect to flash attention become very, very high, and the performance drop is minimal because you are keeping a lot of information around. I will share with you guys this slide, so I mean, let me know if you have questions, but these are the main intuitions. And in the paper, you see some of those ideas. Awesome. I think we can go very quickly over the results. The paper contains everything, but we tested all of these ideas in many different scenarios. The typical ones that you see people testing their models, like associative recall, synthetic task. We see that BMojo with the external eidetic memory is much better than BMojo F if you have associative recall tasks, and you can effectively recall a lot of information from the past, especially in this case. But the main question that we answered in our paper is to understand the scaling laws of these systems, because obviously it's not obvious that this system can scale. So we tried it, and we scaled these models up to 1.4 and then increased a little bit more. And you can see that the scaling laws are comparable with other models, but ours compared to hybrid models are much better. The Mistra that you see here is like our transformer reference model, which has a very long context window, so that is very, very expensive. And it's like our upper bound in some sense, because if you could do attention on the whole context, obviously that's better, but you cannot, and you need to be clever about what you do. And this is like the scaling laws. And there is no saturation that we observed, and the model continuously improves, which basically means that hopefully it can scale even longer and for larger models. We have standard results on zero-shot evaluation. Don't want to bother too much about this now, but the most interesting bit, I think, which I want to highlight here is BMojo has a very So when we were discussing about, so we were working on this in the first iteration on May last year before NeurIPS, and our work was one of the first ones doing length extrapolation, which at the time was also the reviewers like were, why do you care about length extrapolation at some point? I think this is kind of very important at this point in time, because you never know, like, so take a reasoning model. The reasoning model can have a context X, but if the model needs more tokens to reason, I mean, you need a longer context. So having a system that at least does not explode after the pre-training context length, and if you know transformers, they do explode because of positional encoding and stuff, they will not be used at all there. So this is a very important property of the systems, and empirically, we noticed that this BMOJO architecture does length generalize, and I think, and we discussed, and we think that this is mostly because we can reduce a little bit the importance on the positional embeddings in our system, because the system uses the information in the state to encode position, and therefore time is encoded there. And this is a nice observation, which is not typical, and it's very relevant nowadays with the reasoning models. Just very quickly, like the span expansion, the results are pretty appealing too. So for example, here, I just want you to show like span expansion, last row compared to full attention, second row. And basically our results on this, I think it's ruler on the right and the long context evaluation on the left. Don't care too much about perplexity. We know perplexity is not optimal, and we show that in the paper for long context. But on other long context tasks, we show that basically our span expansion implementation is comparable with full attention, at least for the models we tested, which were models up to 7 billion, which is pretty interesting. And I think there is no obvious reason not to think this could scale even more. And you know, if you're familiar with the ruler, you will know like the right plot, which is pretty good, given that we don't saturate, we don't go too much, we don't deteriorate the model performance too much. And last but not least, efficiency of the implementation. Like we show that our BMOJO is faster than either like standard transformers like Mistral with sliding window and full attention, and as well as a linearized version like Mamba. I haven't tried with the GLA, sorry, Sony, but I think it will be comparable. So then it's important. So that's interesting. And the very last point, which I believe is worth to mention this point, is this is like the span expanded attention results. On the left, you have runtime, peak is in the middle, and the last one on the right is basically the same, the two plots before put together in the same one. But what I want to show you is that the runtime is much smaller. I think it's 5x smaller than full attention, obviously, because you don't pay the price. But the peak memory increases a bit. And if you check the black bars in the middle plot, compare them with the yellow and blue, which are the full attention and sliding window, our memory footprint increases a bit because we need to store the embedding representations. And I think the memory usage is like 10, 15, or 20% at most more, which is important because you need to know that whenever you're implementing it, and you are not discarding the KV cache. So you gain a lot of time, but you pay a little bit on the memory side if you don't do any compressed representation of the KV cache. Cool. So I think this is like the final summary of what we discussed. Yeah, we already discussed everything like quite a lot. And this is the picture that I would like you to remember in some sense. And the comparison between fading and eidetic memory. And I've left a little bit of slides and papers and pointers here, plus a new one that we worked very recently. It's called Marconi. And basically, I think it's a great idea for reasoning models where you can backtrack during inference. And it's the first work on doing that on hybrid models. And I think now it's at MLCs. But it's yeah, I think it will become more relevant moving on reasoning models in the future. And here you can find more resources. Thanks. So thank you for attention, and I'm finished.
Yeah, I think there is a question from the you can directly unmute here.
Yeah. So yeah. I would like to ask a question that's maybe. Hello, can you hear me? Hello?
Yeah.
Yeah.
Yeah, okay. I would like to ask a question that's maybe a little bit out of the scope of this presentation, just a little. But I feel like I've always wanted to ask this question, and you are very knowledgeable and maybe can answer it. Basically, with all these approaches like attention alternatives with linear attention, Mamba, sparse attention to some extent, and maybe possibly your work too. We're trying to work within the paradigm of transformers where we train, sequence parallel. So and I feel like that's what has enabled the scale to which attention transformers has become today. But I feel like from my experience and from what I've read, it's very hard to make, expressive and very nonlinear finite state recurrent models, such as GLA, and, other linear attention variants that have, unique gates that to make it, fully sequence parallel. We know we have to do, some of the Mamba variants, we have to do chunked parallel, and, some stuff like that in training. Do you think it's possible? Let's say there exists a way to optimize recurrent models without backpropagation through time, and it's unbiased. And let's say we can train them, token per token with a large batch size, um, to to enable us to make recurrent models that are highly nonlinear and state dependent. As you said, it's very important. The finite state is the update is state dependent and input dependent and all the stuff like that. And maybe you can do differentiable dictionary lookup or like fancy stuff like that, with ignoring sequence parallel stuff. Do you think that's a possible future direction, or do you think it's just too good to have sequence parallel efficiency of sequence parallel training, and the information density of that training paradigm? I don't know if that's too much, but yeah, that's it basically.
So let me try to rephrase the question to see if I understood it correctly. So the main question is, do we really need can we basically go beyond like the current parallelization techniques for training on multiple samples altogether? And is backpropagation through time a possibility, even if we know it's sequential rather than parallel? So I think this is a very important bit, and we have already a lot of experiences about the difference between the two from past results. So take, for example, the LSTM world like 10 years ago, or like before the new stuff. So those were fantastic algorithms. They are much more expressive than, more or less, it's finite precision. So they still have a finite state, so they are not perfect. But in principle, they are much more expressive than any model that we discussed so far, right? They are purely sequential, non-linear. They can do whatever they want in some sense. They can do a lot of very expressive function. But the problem is that it's very difficult to parallelize them, right? So you are getting a lot of expressivity, but you cannot really use it because you cannot train it. So backpropagation through time, by definition, is like a bottleneck over time in which you need to pass through in order to share information from the future to the past through the state, backward, right? And there is no way around. So I think there is obviously, it's very important to study this, because if we manage any breakthrough for sequence models, in some sense needs to pass across that bottleneck. And it can be either through some form of eidetic memory, so you don't have a bottleneck, you just copy the memory, as you said, lookup, which is basically what attention more or less does. And eidetic memory in our framework is trying to go to. But while at the same time complementing it with some efficiency for modern hardware. So I think I don't have like an obvious, oh yes, this is the right solution, because it's still an open problem, and I think it will be, still will be moving forward. However, algorithmic improvements is essentially what we are all working for, right? And making sure that we can implement that efficiently in hardware is the difference between making it successful or not. So
All right.
I
Yeah.
answer a little bit.
Yeah, thank you for answering. Maybe I'd like to add a bit to my question. The reason I asked this was recently I found this line of work called real-time recurrent learning, which basically is the goal of the work is to remove backpropagation through time in an unbiased way. And the way you do it is you keep the gradients of the state in relation to the parameters. And there is a way, but it's very expensive because you have to keep all the gradients. And that's why I assume there's a way to make hardware efficient way to do that line of work. Is it will it overtake transformers, you think, or not? Just hypothetically.
Yeah, I would have to see the work. I think if it doesn't scale, there is no way. It must
Yeah.
be.
Yeah, I knew that network. I knew that the complexity scales like cubically with respect to the total number parameter, if I remember correctly.
Yeah.
And then
Yeah.
so for real-time recurrent learning, they focus on diagonal linear, because in this case their scaling behavior is like much better. But I feel like diagonal is like too restrictive, and I'm not a big fan of real-time recurrent learning. I think they have a poor scaling behavior. And I would want
Yeah.
to add a side note that so for real-time recurrent learning is basically it's like a forward mode of the automatic differential.
Yeah.
And for backward and the backward mode is like the backpropagation through time. Yeah. And in many
Yeah.
cases, maybe it is possible to derive a hybrid training strategy that combines both the forward mode and the backward mode of the automatic differential.
Yeah.
Maybe I can add
Yeah.
that.
Okay.
So having a dynamical system which is only diagonal, I mean, you can prove, and I think Ricardo in the last presentation in this series, they were discussing about tracking. And I mean, if a dynamical system which is only diagonal and is on the real number, it's not a complex dynamical system, it cannot have oscillatory behaviors, because the multiplicity of the poles is not 2, basically, if you're familiar with control theory. And this basically means that you will never be able to do things like, I don't know, like keeping track of I think the addition stuff or modulo operation, which is can
I
fix
see.
that with non-linear readout function as we do in our BMOJO, because it's non-linear and then it's non-diagonal, but still you are missing a lot of the important properties of these systems.
Right. Okay. Yeah. Thank you very much for discussing. Yeah. Thank you.
Thanks.
Are there any other questions? Because we are basically running out of time.
Yeah.
Okay, if there are no questions, okay, there's a question from the chatting room. So in the innovation selection mechanism, the paper used prediction error as a measure of importance. While this design is intuitive and effective, have you considered other importance metrics, for example, commonly used attention scores?
Yeah, okay, that's a good point. So we considered, so the idea behind innovation selection can be applied to any scoring mechanism, as you were saying. So for example, Titan, they do a different scoring mechanism. They call it a new model. That's exactly the same idea. Our own is implemented with this kind of norm of the prediction error, because it's similar to what like a Kalman filter would do, and what the online Gaussian processes regression was doing, which I mentioned in the presentation. But in principle, yes, you can do any scoring mechanism you want. The main problem, though, and that's the crux of it, is how to make it efficient. So if you can use attention again, but then remember that this must be implemented very like in the lowest kernels, if you want, like in SRAM, like as close as you can to the chip. So if you start adding a lot of complexity there, then you will pay the price. And it's not sure to me that having a very complex function to pick the residuals brings you a lot of improvements in the final model, rather than something which is a little bit simpler, but still captures the out of distribution tokens that are the one that really surprise the model. And so, for example, in our case, we implemented it with a very efficient implementation, like not super complex, but very effective, and that was enough for our results.
We have another question from Zhixuan. What's the typical size of the eidetic memory after the final token is processed compared to the full sequence length?
Good point. So it's the full sequence length doesn't mean a lot. Let me compare with the sliding window attention, which is the number of tokens that we start from, if you want, in the sequence. So the ratio is basically 1-to-1 in our experiments, or we reduced a little bit the eidetic memory. So basically, assume that you have, I don't know, you want to apply the system on arbitrary length, and that's why sequence length is not very important to describe the model. But you are only allowed to use a span of the attention, if you want, which is 2K. So what I would do, I would allocate, if we are processing very long sequences, more than 2K essentially, I would allocate half of it to the recent past, or 512 if you want, if it's 2K, and then all the remaining to the state, which is not super large, but still a little bit of tokens in the attention span, plus all the others on the eidetic memory. And the eidetic memory obviously can come from the innovation selection, if you want to process everything causally, or if you allow to go back and retrieve, that will take care of the sparse attention essentially bit.
Okay, thank you for your answer. Are there any other questions? Or will be ending now. Okay, thank you, Luca, again for presenting the very interesting BMOJO and the expansion span work. And I think like so hybriding several different attention module like sparse attention and linear attention within a single layer is a very promising future direction to explore. And thank you for your presentation today.
Yeah, thank you very much for inviting me. That was great. Thank you.
Okay, I'll stop recording.